Revision of magnetism and matter. The previous chapter tells us that the magnetic fields that are created, they are only due to current carrying loops. The origins of magnetic fields are current carrying loops or conductors. In this chapter, we are going to see that there exists something called bar magnets, or in general magnets, which also have their own magnetic fields even if no current flows through them. Okay, so uh, the existence of magnetic field can be attributed to the magnetic moments of the electrons which revolve around the nucleus. Every electron is going to have two angular momenta. The first one is due to the revolution around the nucleus, and the second one is called as spin magnetic moment or intrinsic angular moment, but we are not going to talk about that because that part has also been omitted from your course this year. Okay, and when we will go to the next chapter or the chapter on electromagnetic waves, there we will learn that when we have an electric field which is time varying, that also creates magnetic fields. Okay, so we can have three sources of magnetic field. The first one is current carrying loops, which we covered in the previous chapter, moving charges magnetism. In this chapter we are going to take a look at bar magnets or magnets. Okay, so we now start comparing the magnetic fields produced by a bar magnet, which we can visualize and picture, and the magnetic field produced by a solenoid. Okay, and to define the magnetic dipole moment or magnetic moment m bar of a bar magnet, we take the help of solenoid, because magnetic field created by a solenoid can be controlled, because we know very well that the axial magnetic field is directly proportional to current. So in general, we can say that the current depends on, the magnetic field depends on the current flowing through the solenoid. Okay, so this is the pattern. This is the pattern of magnetic field lines near a bar magnet and also near a solenoid. And what you see here is that the resemblance between the fields, immediately you can, that's clear. So if we first put a bar magnet somewhere, we decide the location, we measure the magnetic field somewhere on its axis, let's say somewhere here. Okay, and suppose this distance is x. Suppose this distance is x. Okay, and then we replace this bar magnet by by a solenoid, and if I take a point x here, okay, which is at the same distance x from the center of the solenoid. By center I mean it has equal number of turns on either side, and if we adjust the current, as long as the magnetic field here matches with the magnetic field that we obtained here, then we can call this solenoid to be an equivalent of the bar magnet. And then the magnetic dipole moment of the solenoid can now be considered as the magnetic dipole moment of the bar magnet, and that is how we define magnetic dipole moment of a bar magnet. Is that clear? Same geometry, same location, same field by two different agents, bar magnet and solenoid. Solenoid, we know very well how to calculate the magnetic field. In the previous chapter's revision, I showed you how that expression due to a current carrying loop, okay, how the magnetic field at this location x, okay, how we modify that when we take this distance to be too far from the center, so that radius can be considered to be pretty small compared to a, pretty small compared to x. Okay, so this is the approximate expression. B bar is equal to mu naught upon 4 pi 2 m bar upon r cube. Okay, 2 m bar upon r cube, and then you can have the equivalent bar magnet. Okay, next, if you now place a magnetic needle, which is also a dipole now, north south, if you place it in an external uniform magnetic field, What is the position of the stable equilibrium? Okay. Yes, the stable, no, there are two positions there. Yeah, okay. Stable equilibrium refers to magnetic moment and magnetic field being like parallel in the same direction. Okay, now stable equilibrium means if you disturb the bar magnet, okay, or disturb the equilibrium of the dipole, it will return to the magnetic field if it is in the air, because there are dissipative forces which will diminish the magnitude every time. Okay, now what is unstable equilibrium? What is unstable equilibrium? Unstable equilibrium is when the magnetic dipole moment m bar and b bar are unlike parallel. Now what is unlike parallel? Okay, like parallel means south to north is m bar, okay, and this is sort of north to south. South to north. Magnetic dipole moment is always from south to north. Okay, and this is b bar in either of the cases. This is b bar in either of the cases. Okay, so दूसरा केस मध्ये unstable equilibrium, that means it is still equilibrium, but the moment you disturb it slightly, then it will again uh, be pulled towards b bar. Okay, fine. Now because tau bar is equal to m bar cross b bar, because tau bar is equal to m bar cross b bar, we have seen this expression for current carrying loop placed in an external magnetic field. But because we have now arrived at a conclusion that there always exists an equivalent solenoid for our bar magnet, a bar magnet or a magnetic needle for that matter will also experience a torque given by m bar cross b bar, where m bar will be its own magnetic dipole moment. Okay, so using the scalar form, we may write the magnitude of the torque as mb sine theta, and using the fact that if theta is very small, then sine theta can be approximated as theta. So sine theta can be approximated as theta, so the torque will be mb theta. Okay, and this will actually lead to angular harmonic motion, approximately angular harmonic motion. So for simple harmonic motion, it is a to and fro motion of the mass due to spring. In this case, it is angular harmonic motion, so it will be like this, 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 like a pendulum. Okay, it will be an angular harmonic motion, and its differential equation is given by remember, if you remember, for the simple harmonic motion, it is m d2x by dt squared plus kx, the restoring force due to spring, is equal to 0. This is SHM. This is angular harmonic motion. So instead of mass, you have moment of inertia. Instead of linear acceleration, you have angular acceleration, theta double dot. Theta double dot means second order derivative of theta with respect to time. Plus mb theta is equal to 0. What is mb theta? It is the restoring torque. Okay, it is the restoring torque. So every time you pull it back from its equilibrium, it will the mb theta thing will again try to push it towards the equilibrium position, and that's how the angular harmonic motion is set. Okay, so if you have this expression, then you can actually determine the angular frequency. Okay, or angular frequency, how many radians per second it is covering, and that is given by omega is equal to root of m into b upon I. Okay, and if you take 2 pi into reciprocal of this, then you can very easily determine the time period. And in fact, time period is easy to determine, and using this, okay, you can determine the magnetic dipole moment, and if magnetic dipole moment is known, you can actually determine the magnetic field in which your needle is oscillating. Okay, so depending on what parameters you know, you can determine the value of the unknown parameter. I is geometric, it's not current, it's moment of inertia. Okay, you may want to revise your rotational dynamics concepts if you want for understanding what moment of inertia is. Okay, but I hope that's not a big deal. Okay, so is that clear? Yes. Okay. Now you can also analyze the same situation using energy approach. Okay, so how do you define potential energy, magnetic potential energy? Um is equal to integral torque d theta, and that torque is mb sine theta. That torque is mb sine theta, and if you integrate sine theta you will get negative cos theta. So it will be negative mb cos theta plus c. Now how to deal with the constant of integration? To make the constant of integration 0, okay, to make the constant of integration 0, what do? We take theta to be pi by 2 and we assign 0 potential energy. We assign 0 potential energy for what? We assign 0 potential energy when the magnetic dipole moment and magnetic field are perpendicular to each other. At theta equal to pi by 2, we say is 0. And this allows us to define magnetic potential energy as negative of the dot product of m bar and d bar, where theta is the angle between the two. Okay, now if you go back to first chapter, electric charges and electric fields, there you will find that potential energy of an electric dipole kept in a uniform electric field is negative p bar dot e bar. Okay, and here you are talking about magnetic potential energy um. Even there we had chosen the same reference. When theta is 90, we had chosen the potential energy to be 0, because again for potential energy we are only interested in the change that happens in the potential energy and not the actual value. Okay,
potential energy
and
equilibrium मध्ये असतात करना नाही
if you want, you're talking about the situation where the potential energy is the least, that will always refer to stable equilibrium position. Got that? Now least doesn't necessarily mean zero potential energy. So when is it least? It is least when it's u min. So this is u min. Okay, and unstable equilibrium is when the potential energy is the greatest, and that is mb, that's u max. Is that clear?
पण स्टेबल इक्विलिब्रियम मध्ये थीटा 0 असतो ना.
हो ना, पण मग थीटा 0 असेल तर cos theta 1 नाही का होणार?
पण मग pi by 2
But that is the reference that we have chosen for zero potential energy, so that constant of integration becomes 0. Okay, see, because when you let theta to be 0, um will be equal to constant of integration, right? If I choose theta to be pi by 2, cos theta will be 0, um will be equal to c. Correct? So at that location, at that orientation rather, I would say let potential energy be 0. It is analogous to saying on surface of earth potential energy is 0. I could have also chosen somewhere here as my reference, right? Always remember, potential energy always requires a reference, and everything is measured with respect to it. Okay. For electrical potential energy, if it is a point charge in an electric field, at infinity we take the potential energy to be 0, right? Okay, cool. So having so many analogs, Gauss law, Ampere's law, Coulomb's law, Biot-Savart law, let's now talk about dipoles, specifically dipoles. Okay, fine. Yes. Hmm. Yeah, there, okay, see there you don't need any reference. म्हणजे तो रेफरन्स दोन्हीकडेच येणार आहे. जस्ट लाईक इन डेफिनेट इंटिग्रेशन कॉन्स्टंट ऑफ इंटिग्रेशन डज नॉट अपियर, तसंच तिकडे पण आहे. कळलं ना? जसं की इथे कॉन्स्टंट ऑफ इंटिग्रेशन मॅटर्स, बट if I say 1 to 2, then does it matter? No, it doesn't. Clear? It's that. You're absolutely right. What you said is right. There is one more formula for work done, and that work done basically is change in potential energy. But again, it becomes a definite integration problem because you know the original, the initial, and the final orientations, isn't it? So then C doesn't play any role there. Okay. Yeah. Got it. Okay. So what are the analogs as far as this dipole moment is concerned? In electrostatics, the constant of proportionality in the Gauss law is 1 by epsilon naught, whereas in magnetism, the constant of proportionality is mu naught for Ampere's law. Okay. Okay. Next. Dipole moment, here you have P bar, here you have M bar. The SI unit of electric dipole moment is, can you tell me the SI unit of electric dipole moment? Coulomb meter. No. Electric dipole moment is Coulomb meter. Magnetic dipole moment is Ampere meter. Correct. Okay. Equatorial field for a short dipole, negative P bar upon 4 pi epsilon naught R cube. For magnetism, electric equatorial field, negative mu naught M bar upon 4 pi R cube. Okay. Axial field 2 P bar upon 4 pi epsilon naught R cube. In this case, it is 2 M bar into mu naught upon 4 pi into R cube. Torque is P cross E, M cross B. Energy is negative P dot E, that is negative M dot B. Okay, so you will understand these analogs better if you work them out on your own. We have already done that in our regular classes. Okay. See, but the thing is, in magnetism, you have solenoid to compare your bar magnetism. But here you just have 2 point charges. That's it. There are no equivalents in electrostatics as solenoid and bar magnet. But anyways, with that you can say that in electrostatics you can have isolated positive charge and negative charge, but in magnetism you cannot have that. Every north pole will have to have its partner south pole. Okay. Alright. That's why magnetic field lines are closed lines. Electric field lines, they originate and terminate at positive and negative poles respectively. Alright, next, Gauss law. Now this Gauss law is of magnetism. Gauss law of magnetism. It tells us that if I have a closed surface, okay, if I have a closed surface, then the surface integral of the magnetic field taken over that closed surface E is always equal to 0. Okay, the surface integral of the magnetic flux is always 0. Okay, because well, this is a proof or another way to state that magnetic monopoles do not exist. Okay, magnetic monopoles don't exist, or at least they are not yet found. We can say they may exist, but they're not found yet. So this Gauss law of magnetism still holds. Okay. Okay. Now the main part, whose mathematics is there in your syllabus, that is magnetization and magnetic intensity. So we know that in any magnetic or even non-magnetic material, you will have electrons, and every electron is going to have its own magnetic moment. It's a vector quantity. So if I consider magnetic moments individually of all electrons, and if I add them vectorially, what I will get is the net magnetic moment of that material. And if you divide this vector by a scalar, which is the volume of that element, okay, or of that bar or ball, whatever that object is, then you get a quantity which you call magnetization. Okay, so a capital M bar is called magnetization. The SI unit of magnetization will be SI unit of magnetic moment, that is ampere meter squared, divided by SI unit of volume, so it will be ampere per meter. Is that clear? Okay. Now to measure the magnetization, we first imagine a solenoid which is carrying a current I, and well, we know the magnetic field due to the solenoid, the actual magnetic field, it will be mu naught Ni. And if I now place an iron rod, which is a ferromagnetic material, inside, then I will find that the magnetic field is enhanced tremendously. Okay, the magnetic field inside is enhanced tremendously, and that is due to an additional component of the magnetic field, and that comes from what? That comes from the material, Bm bar. This is due to the material getting magnetized. The material getting magnetized due to this. Okay. So we now start writing the following. We say magnetic field total is coming from two things. Number one, due to this current, which was already there, and number two, the material. Okay, and we say that the net magnetic field is mu naught times magnetic intensity h bar plus mu naught times the magnetization m bar. Okay, this is the definition. Okay, the magnetic field inside is mu naught into magnetization per unit volume. Okay, or the net magnetic dipole moment per unit volume, or what we call magnetization. Then we relate magnetic intensity h bar and magnetization m bar by this relationship. M bar is equal to chi h bar, where chi is called as magnetic susceptibility. Chi is called as magnetic susceptibility. And the value of chi with its sign, SIGN sign, determines whether it is a diamagnetic or a paramagnetic or a ferromagnetic material. Okay, so if you write magnetization as chi times the magnetic intensity, you can take magnetic intensity common and you can write it as 1 plus chi. This 1 plus chi is called as relative permeability mu r. Mu r is called as relative permeability. If you remember, we also have a term called relative permittivity. Okay, and that relative permittivity has another name called dielectric constant. Okay, anyways, so if you take the product of permeability of free space into the relative permeability of that medium, okay, or of that material, then you get the actual permeability of that medium. So mu naught into mu r is mu. So how many new quantities have we introduced here? Magnetization, magnetic intensity, magnetic susceptibility, and the fourth one is relative permeability. So I hope you understood this part, or no? The enhancement of magnetic field is because we insert a ferromagnetic material here, and that magnetic field is found to be proportional to magnetization. This Bm bar is found to be proportional to magnetization, with constant of proportionality being the permittivity of free space. That's why this has come. Okay, all right. If the magnetic susceptibility is small and positive, we get paramagnetic materials. If it is small and negative, then it is a diamagnetic material, and if it is large and positive, then it is a ferromagnetic material. Diamagnetic materials show weak repulsion towards magnetic field. Paramagnetic materials show weak attraction towards magnetic fields, and ferromagnetic materials show strong attraction towards magnetic field. Now what do I mean by that? Strong attraction means they prefer to be in a region of stronger magnetic fields rather than in weaker magnetic fields. Weak repulsion of diamagnetic materials means they prefer not to be in the region of magnetic field than being in the region of magnetic field, or they try to be in a region where external magnetic field is weaker. Okay, all right. Yes, so if these are the field lines, let's say the uniform field lines, if you place a diamagnetic material in between, the net magnetization inside, okay, is such that it opposes the external field. Therefore the field inside is weakened. That means B naught bar and Bm bar are in the opposite direction. Okay, are opposite. B naught bar is the original magnetic field and Bm bar is the response of the diamagnetic electrons of the diamagnetic material. So its its magnetic susceptibility is between -1 and 0, and if you add 1 to both the sides, all the sides, then you will get the relative permeability, and the actual permeability of the paramagnetic material or paramagnetic substance is less than that of vacuum. Okay, now when chi is exactly equal to -1, we get what we call superconductors, and the phenomenon where the electric susceptibility is -1, or the magnetic field inside that substance is totally zero for superconductors, that effect is called as Meissner effect. That effect is called as Meissner's effect or Meissner. If you take superconductors whose electrical resistance is zero, okay, so they don't get heated when electric current passes through them, they also possess another property. And what property is that? The property is, if you place a superconducting material inside a magnetic field, okay, inside a magnetic field, then the magnetic field inside the superconductor is totally zero. For diamagnetic it is weaker than outside, but for superconducting it is totally zero. Okay, that is my yes, that is my side. Okay, for paramagnetic materials it's on the other side of the spectrum. That means diamagnetic materials prefer weaker fields inside of the same value as paramagnetic materials prefer stronger fields. Okay, so you can see these bending in the lines. This bending in the lines represents enhancement of the magnetic field inside. But if you have numbers, then the enhancement is extremely small. I think 1 in the factor of 10 raised to 6, something like that. It's extremely small improvement in the original magnetic field inside. Okay, so the magnetic susceptibility of paramagnetic materials, it is positive, but it's very small. Epsilon is very small number. Epsilon is a very small number, not to be confused with permittivity. Okay, please remember that epsilon is not permittivity in this context. What is that? That is a very small positive number. Okay, but positive. Okay, then you add 1, and you can say that for paramagnetic materials the permeability is greater than that of vacuum. Okay, and for ferromagnetic materials we have a theory called domain theory to explain that, where there exist regions within I just refreshing it. There exist regions in the ferromagnetic materials where the magnetic moments naturally merge together, and they have a very large magnetic moment resulting for that specific region. So what happens if you keep a ferromagnetic material inside magnetic field is that these domains, we call them domains, these domains merge together. Which domains merge together? Whose magnetic moments are along the magnetic field, and those domains vanish or shrink whose magnetic moments are opposite. That is why when you place a ferromagnetic material inside a solenoid, when you place a ferromagnetic material inside, the magnetic field is enhanced tremendously. Okay, all right. I think that more or less completes everything that is mathematical here. Curie law has been omitted, right? Curie law is not there. Yeah, okay. नहीं है, ठीक है. Last part. We'll discuss hysteresis quickly in 1 minute. Hysteresis refers to lagging of magnetic field inside a ferromagnetic material even when the external source of magnetic field has been switched off. Okay, so I'd like to mention three situations. Okay, let us say we start initially unmagnetized ferromagnetic substance and we try to magnetize it. What we find is uh, the magnetic field inside will increase and at a certain level it will saturate. So even if you increase the external magnetic field, it will not show any increase in the net magnetic field inside the ferromagnetic material. Okay, now if you try to decrease this, if you now try to start decreasing the external magnetic field or magnetic intensity, it will not follow this path, but it will follow some other path. Okay, so the moment where your external magnetic field is zero, magnetic intensity is zero, the magnetization is retained. Okay, the magnetic field inside is not zero, and this point refers to, or this value here refers to, retentivity or remnants. Okay, this is retentivity. So in order to nullify that effect, we have to send current in the reverse direction, okay, to make it zero. So this is the point C. Okay, and the value there of magnetic intensity is called coercivity. And the same behavior is shown on the other side of the loop. Okay, C to D, then D to E. So E again refers to retentivity. Okay, and this point here, not mentioned, but let's say F, that will also show coercivity. Okay, and then considering the area of the hysteresis loop, you can choose the material. If you want to minimize hysteresis losses, then you, like in transformers, then you would like to prefer substances which have thinner hysteresis loops.